Today I am going to discuss application of mutual exclusion principle in group theory. Now, what is this mutual exclusion principle? This principle says that if a molecule has center of symmetry, that if molecules contains I symmetry element, then all vibrations of this molecule which are Raman active will be IR inactive and vice versa. Now, to understand this principle in group theory, I am taking the example of trans N2F2. This is the structure of trans N2F2. Okay, or lone pair you can represent like this. And symmetry elements present in this N2F2 are E, C2, I, and sigma H. Now, to understand this concept, that is mutual exclusion principle in group theory, we need to find out vibrations, because this is something related to the vibrations. So first we need to find out the vibrations or vibration modes for this trans N2F2 molecule. Now, to find out this vibration mode for this trans N2F2 molecule, the first thing that we need to do is to find out or to determine the reducible representations for this trans N2F2, and then we will convert this reducible representation into irreducible representation form, and from there we will find out vibrations or vibration mode for this trans N2F2 molecule. Now, first target is to find out reducible representations. For this, what we need to do? The point group for this is C2H. This is the point group. It has E, it has C2, it has I, it has sigma H. Now first we will find out contribution per atom. That per atom, that each atom how much contributing in the reducible representation. So contribution per atom, I am writing CPA, short form, contribution per atom, and that is determined from the matrix, and actually that is equal to the character of the matrix corresponding to these symmetry elements. For E, this is 3. For C2, this is value is -1. For I, this is value -3, and for sigma H, it is 1. After that, we need to find out the number of unshifted atoms when these symmetry elements are performed on this molecule, that is unshifted atoms. Now, if I perform E on this molecule, E means doing nothing with the molecule or 360 rotation. When E is performed on this molecule, all the 4 molecules remain in its actual position. There is no shifting of the atom in this molecule. So for E, it is for this number of unshifted atom. For C2, if you will carry out the C2 is this one. If you pass this plane axis from here and you will rotate about that 180 degree centigrade, all atoms will exchanged and there will be 0 unshifted atom. For I is inversion of all centers. In this case also, the number of unshifted atoms will be 0. And then sigma H the molecular plane, which is perpendicular to the principal axis. If you see the reflection of this molecule in the plane, you will find that no molecule is changing its position. That means the unshifted atoms will be 4 here. Okay, now what is I have to do? Now I have to find out the character of reducible representations. And this character of reducible representations is actually equal to the product of these two, contribution per atom and unshifted atom. For E, it is 12, C2 it is 0, I it is 0, and from here it is 4. So this is my character of reducible representations that I have to use. Now this character of reducible representations then described or determined in terms of reducible representations, and for this a formula is used which is like this: n is equal to 1 upon h summation over I n character of reducible representation into character of reducible representation. Okay, where h is equal to order of the point group. Order of the point group. For this N2F2 molecule, this H is equal to 4. Why 4? Because we know that order is equal to number of symmetry elements present in the point group. In the point group of this trans N2F2, that is C2H, we have 4 point symmetry elements E, C2, I, sigma H. Therefore, the order is 4. Now this N, what is this N? This N is the, you can say, constant which appears before these symmetry elements, which is written here. For E this is 1, for C2 it is 1, for I it is 1, and for sigma H it is 1. Okay. Now what we will do, we will use the character table and we will deduce this reducible representation in terms of irreducible representations that we have to find out here. That is, this is the reducible representation and these are the irreducible representations. These are the irreducible representations for this C2H point group. Okay. Now I will use that reducible representation, which was this one. This is equal to 12, 0, 0 and 4. I will use this one to find out the value of this n for each one irreducible representations. So for an AG, it will be equal to 1 by 4, that is order, then bracket start, then for E n value is 1, then character of irreducible representation, this is also 1, into character of reducible representation. For E it was 12 plus 1 into 1 into 0. This one is n, which is 1 here. This one is character of reducible representation. This is also 1, and this is 0 from the reducible representation, plus 1 into 0 plus 1 into 4, because the value of reducible representation for sigma H is 4. Now when you simplify it, you will get 1 by 4 into 16, that is equal to 4. Likewise, we will find out for this second irreducible representation, that is BG, and BG, and this NBG is equal to 1 by 4, then 1 into 1 into 12 plus 0. Since when you multiply any number with 0, you will get 0. So we here is 0, because in reducible representation the value of C2 is 0 and the value of I is also 0. Then plus 1 into minus 1. Here for this BG, the irreducible representation character for sigma H is minus 1, and into 4. If you will solve this, you will get 1 by 4 into 8. This is equal to 2. Same way for AU, This will be equal to again 1 by 4 bracket start. Now see the reducible representation corresponding AU 1 1 minus 1 minus 1. So 1 into 1 into 12, then again plus 0 and 1 into minus 1 is minus 1. Okay, this is minus 1 corresponding to AU into 4, and again here you will get 1 by 4 into 8 is equal to 2 and AU. Okay, in the same way we will find out NBU and this is again equal to 1 by 4 bracket starts, then 1 into 12, then plus 0 and plus 1 into 4, and then if you will solve, you will get 1 by 4 into 16, 1 by 4 into 16, this is equal to 4 and BU. This is equal to 4. So from here we have obtained total modes, and which are equal to 4 AG plus 2 BG plus 2 AU plus 2 BU. Okay. Now our target is to find out vibration modes. We know that vibration modes are equal to total modes minus translational modes plus rotational modes. Now, what is these are translational modes and rotational modes? Now, these modes can we find out from character table that I have shown you. This is the character table. From here, we can find out translational modes and rotational modes. To find out translational modes, we use this X, Y, Z, and to find out rotational modes, we used this RZ, RY, RZ. Okay. The molecular symbols, these are the molecular symbols corresponding to X, Y, Z. They represent the translational modes, and the molecular symbols corresponding to RZ, RY, and RZ, they represents the rotational modes. If you see from here, this X is corresponding to the BU, then BU will represent a translation mode. Y is corresponding to the BU, then again BU will be the another translation mode, and Z corresponding to the AU. So here we have 3 translation modes. One is AU and 2 BU. Okay. In the similar way, this RZ is corresponding to BC, then it is our rotational mode. Again RY, this is also corresponding to BC, so this will be our another rotational mode. From here you see RZ, this RZ corresponding to AZ, so it will be our third rotational mode. So here we have 3 translational modes and we have 3 rotational modes. So what are the translation modes? T modes, that is translation modes, these are equal to AU plus 2BU, and the rotational modes, these are equal to AZ plus 2BC. So from here, vibration modes will be these total modes minus summation of these two. If you subtract, you will get, since 4AZ, 1AZ, 4 minus 1 is equal to 3AZ plus 2BC, and here also we have 2BC, so cancel out, there is no BC remain. Now 2AU and 1AU, we will left with 1AU plus 2BU, this is not, this is I think 4BU, this is 4BU minus 2BU, then we will left with 2BU. So these are our vibrational modes. Okay, we can also justify over these modes using a simple formula, that is degree of freedom formula. We know that total degree of freedom is equal to, we know this is 3n, where n is the number of atoms present in the molecule. In trans, N2F2, n is equal to 4, so it will be 12. Okay, and vibrational modes, since molecule is non-linear, it will be equal to 3n minus 6. So 12 minus 6 is equal to 6. So in this molecule, we should have 12 total modes or total degree of freedom, and we should have 6 vibrational modes. Let's see from here. Total modes, they will represent total degree of freedom. If you see, 4 plus 2 6 plus 2 8 plus 4 12. So 12 here. If you see vibrational modes, 3 plus 1 4 plus 2 6 vibrational modes. Okay, so our answer is correct up to here. Now what we have to find out? Now we have to find out that among these, which one is Raman active, which one is IR active. For this, we again need to use our character table. Okay. Now we will use our this region as well as this region. Now the modes, or you can say molecular symbols corresponding to these terms Rx, Ry, Rz, Z, Xy. Okay, they represent a molecular symbol corresponding to these X, Y and Z. They represent vibration modes, that is IR modes, and these terms here, this region, they represents the Raman active modes. This represents IR active modes, and this represents the Raman active modes. Okay. Now if we see from here in our vibration modes, we have 3 Ag. We have 3 Ag. 3 Ag is corresponding to these x square, y square, z square and xy, which is the terms of this region. So Ag is our Raman active mode. So Raman active modes. This will be Ag. Now second is which corresponding to this XZYZ is BZ, but we don't have BZ in our vibration modes, so this will not be Raman active. Okay, so only we have this AG is Raman active mode. Now IR active mode, that will corresponding to X, Y and Z. If you see, Z corresponds to the AU, we have AU in our vibration modes, and this XY corresponding to BU, we have a BU in our vibration modes. So AU plus BU, these are our IR active modes. There is 2 BU and there is 3 AG. Okay, now you see, in vibration modes we have AG, AU and BU, and among these AU, BU and AG, only AG is Raman active and it is IR inactive, whereas AU and BU, they are IR active and Raman inactive. So this justify our mutual exclusion principle, which states that the vibration modes of a molecule, if the molecule has center of symmetry, Raman active modes will be IR inactive and IR inactive modes will be Raman active. Okay, this is the end for today's class. Now you have to do some practice yourself by taking the example. I am writing the example here. Question number 1. This is our H2C double bond CH2. Question number 2 that you have to do is trans 1,2 dichloroethene. Okay, you have to practice these 2 questions by yourself. Thank you.